Hi, everyone. Thanks so much for having us here. It's a great pleasure to be here. We are causaLens. We're based in London, but actually we are remote. So we are based all over the world. So today I'm going to tell you about modeling dynamic systems in Python. And this is a little bit special, this use case. The dynamic systems are special because they're different from static data that are more common. So I think this is a very unique use case, and I expect that we'll have some interesting questions. So let me first begin by introducing a little bit about us and our company. So we focus on dynamic systems, and in particular, we focus on time series. So what are time series? They are data that is generated with a timestamp. So it is data that has a sort of a time component associated with it. So they can be generated all over. They are generated. They are all around us. You have things like sports watches on your wrist that generate a real-time data about your heart rate, your breathing patterns, your all of those things. You've got system logs streaming all the time in the cloud. You've got financial markets, which are continuously updating with new prices, new trades, things like that. All of these are time series. They can be in form of numbers, or they can be some kind of structured data. But essentially, they're what we would call time series. And there is an estimate that by 2020, there will be 50 billion devices worldwide generating real-time time series. So most of this is driven by Internet of Things. So small devices embedded all around us, sensors in buildings, smart buildings, things like that are generating real-time data. So time series data measure how things change over time. And we, as a business, focus on predicting the future of time series. So given some data on, let's say, a stock market price, we want to know what that price will be sometime in the future, maybe. Or given a failure data in a data center, we want to know what will be the failure rate tomorrow. So what does a prediction problem in time series look like? It looks something like this. So here's an example. This is a mortgage rate, how much annual percentage you pay on a house loan. And so you can see that actually changes quite a lot. And this is a time series that can go back 50 to 100 years. And you're very interested actually in understanding what's going to happen to the mortgages in the future. If you are, for example, a credit company, if you provide mortgages to people, you really want to know what's going to happen to mortgage rates in the future. So how do you actually predict what's going to happen? Well, you build a machine learning model that is going to try to predict, let's say, this data point here, given the data from a year before that point. So that would be an example of a time series prediction problem. And we'll go into the details of how that actually works. But the point is that there is this time gap between the time when you're trying to predict something and the data that you're using in the past. So I might be predicting, I might be here, today might be 2016, and I might be predicting what's going to happen in 2017. So this is actually extremely hard to do, right? Why is it hard? It's hard because the causal factors are changing in real time. What is it that drives mortgage rates? Well, all kinds of things drive mortgage rates in the world. For example, the interest rates set by the central banks. Or, for example, the amount of loans on the market, the housing prices. All of these things affect mortgage rates. And so being able to predict this is hard because these factors that are really predictive, these leading indicators, they are causal and they're changing, and we don't know what they are. there's also all kinds of other problems. The data might be dirty. It's coming in real time, and it might be dirty, and it might have issues. A sensor that used to work stops working, starts emitting a constant value, right? Your predictive model has to update to take that into account. It needs to be robust to a failure like that. Moreover, the world is a very complex place. You've got millions of financial instruments, for example, or you might have millions of devices all over the world that you might be interested in modeling. So you not only have to do this, which is a hard problem, but you have to do it at scale. So you need to be able to handle thousands and potentially millions of models in real time. Right now, you can do this manually. You can build scripts to build this, but it is slow and expensive to do it one at a time. So, and the performance is not optimal. So our solution is about building this at scale. So solving this problem, not just once, and not just in one case, but in a case of thousands of models. So that's what we do. We build predictive technology for complex and dynamic systems, and we'll get into the details of how we did. So this is a kind of a big picture overview of our product. There's Python all throughout the product, but I want to give you first, before we jump into the Python, I want to tell you a little bit about the kind of the product as a whole. So as I said, this is about predicting the future. And so we've got, the way we do it is we phrase it in language of time series. So there's this step before you get to time series. That step is where you extract data and convert it into time series. So you might be actually looking at, for example, real-time video. This is a common use case if you're trying to predict sales. You might have a camera sitting in front of a shop measuring how many people pass by the storefront, right? That data, there's all this complexity of doing computer vision and measuring how many people pass by, right? But once we've measured and aggregated that data, we end up with something like a number. For example, in the past minute, there was 53 people who passed by the storefront, right? Or we could do all of this complicated measurement of figuring out what is the weather outside, but we could also produce a time series, and we could say, well, it's sunny outside, or it's cloudy. So that would be like a categorical time series, a time series of labels, the tags. You know, it's sunny right now, 10 minutes later, it's cloudy. That's also a time series. So you could extract all of these. You can extract natural language in form of a time series. You can, for example, take a tweet, somebody saying something positive about a certain company, or somebody saying something negative about that company. And you can convert that sentence that has a positive sentiment into a positive number, and the sentence that has a negative sentiment into a negative number. So once you've done all of those bits, you've got a data set of time series. And that's where we jump in, and we do all of this work at producing a predictive model. So a few quick comments about how that's done. We automatically align and prepare the data, and Senad will tell us how we do that. We also do feature engineering and selection, and Senad will cover that bit as well. We won't really talk about these other bits, prediction, how we do it, how do we select algorithms to do it, how do we optimize hyperparameters. All of those are super interesting questions, and we'd love to talk to you about it. So please, if you're interested, please come and talk to us. But our solution really is there to try to do this in real time and to do it automatically. Because we need it to be automatic, because we need it to scale. And for us, scaling is in terms of human effort, right? We don't want to be looking at models, because if there's millions of them, we won't be able to look at all of them. There's too many. So a few comments about Python. Senad will go into a lot more detail, but I wanted to say that there's some, it's all really connected with Python, and Python has been really great in enabling us to do this today. So we've got a lot of numerics in the background. Most of it is driven by NumPy. We've got all kinds of analytics and machine learning that we use as well. sklearn is really a great library. XGBoost as well. There's some specific time series stuff here. I'd like to point out, for example, Facebook's Prophet. That's a time series prediction library. There is ARIMA. ARIMA is a type of a model for time series as well. On the more kind of data side and on the web side, we use Django. So we heard a great talk just previously from Israel about Django. So that's what we do as well, and that resonated with us. We also use Gunicorn and Redis and Postgres. Oops, sorry. So ultimately, this is what we're trying to build, this device right here. Well, we kind of have it as a picture of a hardware device, but it's not really. It is a piece of software that is sitting there. It looks like a CPU. We call it a CLPU. And it's sitting there, and it's absorbing real-time data, and it's producing real-time predictions. And so it is incredibly scalable and incredibly ambitious. So that's what we're trying to do. And it's scalable in a lot of failure modes. So for example, one of those inputs might suddenly break, and we expect this machine to continue to work. So with that, I would like to stop and let, I do want to say a little bit more about that device. So like I said, fully scalable and autonomous. So you can pipe hundreds of time series into it, and not all of them might be relevant, but it's going to figure out which ones are. It's going to also deal with cleaning the data in real time, which means it can handle things like this, like if your sensor has suddenly broken, it's able to build a process to clean that in real time. You can deploy it on any device. It's scalable, real time, and most importantly, it adapts to a changing world. So if something changes, for example, going back to our example of mortgages, if something changes to the underlying world about how the mortgages are issued, we would expect a mortgage model to understand that and to adapt to it. So that's really the vision that we have of the product that we want to build. So, so with that, I let Senad speak about the building blocks of the system.
Hey guys. So I'm Senad, and I'm a software engineer at causaLens. And so I would really like to tell you a little bit more about how we structure these things. It's kind of always evolving. So we are a small startup. So everything is written in such a way that we can either change it, evolve fast, or even sometimes remove it. So this is basically the layout of our stack, and everything is written in Python. I will talk a little bit more about the components of each one of these and what we use. For example, so let's go bottom up. So in order to store all this kind of data that is being generated, we have to have a file system that is able to do that. So this file system is basically file. It's really, really intuitive. So you have the files, you have the directories, and then you have the content of those. And of course, what you do also have is you have metadata information. You also have audit trails, how the thing got there, and so on. So what's really important about it to say here is that we actually separated the file and the content, because you may not even have the content when you actually have file, because the data is coming as it is. And And therefore, what we do here, we use polymorphic models. So we use polymorphic models here in order to abstract away the storage backend so that your files can be anywhere. So we keep files everywhere, almost like you have it in database. You can use your file system locally, which is really great. For example, we have people that really would like to try this, so you can kind of ship them a virtual machine. This is fully installable. The entire thing is installable on a virtual machine, so you can, send it to them, and basically it can save the content on the local file system. It also supports S3 and Google Cloud Storage, and on top of it we have basically this is the object store, where some of these parts are actually, this is a thin layer, but some of these parts are actually in the services layer, and some of them are related to the file system. But it's kind of logically separated here. It's not the actual image of the things. So you have a service here, basically, which provides the object API. So this is what is available. We have actually a public API wrapper on top of this. It's basically a simple proxy to the object API. And using this object API, you can basically do the things that you're doing with the simple file system. So you can write, you can read, you can list, and so on. We limited the scope here. If we talk, maybe if we had time, I will tell you how we limited the scope, because we don't do any difficult recursive operations. That there's no need for that. And here we also have a Fuse API, so you're able to mount our file system on your local machine and use it basically from your, browse files from your computer. And now we have a service layer. So these services are, well, not in the sense that they are separated anyway. All of these services are just Python packages that can be installed on its own, and they can then expose the API. You actually never use them directly, you always use their API. Their API can be just so you can start the logic and have an API class, and basically each of these services can implement this class, and you can use it without touching other services. So this is the data, the models, everything is sandboxed. They do not share foreign keys or something like that. So everything is sandboxed, models are sandboxed as well, and you provide an external API. So you can use it that way, but what's really easy, you can attach tons of URLs basically on this, and you will get actually a REST service. It's quite difficult to go further from there. A really cool thing that we do here is job service. So we are running a lot of jobs that need to analyze this data. So these jobs can run either on Celery, which is really great again for virtual machines and even Docker and so on. But what's really great also, when you get these models that are really important, they kind of when you get the model, it's really fast to get the next prediction for it, and you can run it as a Lambda basically. Or you can even use Fargate. You create a task definition, and you can use Fargate for that as well. And so there are a lot of services there. And what's really important, okay, so there's an API layer, and on top we have UI, which is Django and Vue.js. We started using Vue.js recently, and I kind of like it a lot. I'm not even a front-end engineer, so I like it. So, and this was really important. This is the meat of the matter. Those are not services, but they are actually libraries that we provide. So when you operate with this kind of data, you have to have there's a lot of there available with libraries like NumPy, SciPy, and so on. But you have to wrap this, as always, to fit your logic. So we have different kinds of libraries for columns, dataset, matrices, and modeling. So the data actually comes in different resolutions, so we'll talk about that. And you have the algorithms that you're using, and so on. And I would actually use this opportunity to answer the first question. So yes, we use LSTMs so we use LSTM, and we also use convolutional neural networks and neural networks as well. So this goes okay. So what tool framework using to file management in terms of tracking version metadata? So we so there's no tool basically that we are using to manage this file management. We kind of didn't know what we will need, so we have basically a JSON structure that contains a dictionary, which is we call it metadata, and we have the same thing for audit, and we kind of have a written written agreement of what can go inside there. For example, the audit information tracks the life cycle of a file and so on. So, but we don't use anything. So it's just attached to a model in a database. Batch versus online. So this is a short slide. I just want to tell you guys that we're going to talk a little bit about online or real-time processing, and I want to make I just want everybody to be on the same page and say that this is different from batch processing. Basically, what we are doing here, we analyze the points as they come in, one at a time. So we are not queuing or doing something like that. We are doing, everything as it comes in. So this is the example. It's like a really simple example. On the right side, you have an example of a time series that is actually generating data. These ticks that happen actually are really important because they can be milliseconds, seconds, minutes, days, weeks, years, it doesn't matter. So this is what is really important. This is what's called the resolution. So how your data is coming in. And so you really need to know how to do buffering very well if you need it. And you need to know, for example, when to emit new points and so on. And what is really important for the Python crowd is that we do compute online. And we do compute on Windows. And NumPy basically cannot do that on its own. So we kind of had to create our own wrapper a little bit around create our own structures that allow us basically to do this operation. For example, if you are interested in calculating something on a time span and you have incoming data, you really have to worry about the state of this. It has to be fault tolerant, for example. Somebody pulls the plug, so it has to persist the state in some way, and these points are analyzed one at a time. And what's really important is that machine learning algorithms that we also do, we have this online adapter that allow them to actually run online as well. Okay, so in order to go to the meat of the matter, I have to define something. So I'll be really quick about it. So basically, if you have any kind of data and you want to learn something from it, or how will it behave in the future, you really want to know what are the features of this data. Basically, what are the driving indicators that drive that phenomenon forward. So this process is called feature engineering, where basically you can also create your features, you can check how those features work with your model, or improve the features if needed. And so, for example, if you remember the slide from below, basically something that's really important, perhaps, you can imagine, for example, maybe not in Serbia, but in the West at least, during the Christmas, for example, air cargo traffic will probably increase because people are shipping gifts and so on. So daytime feature basically means that, well, it's Christmas, then probably it's important, and you have these kind of examples all around. You have lagged features where it's important to use the history. Let's say, in order to predict the value for the next month, I want to use the values from the previous 3 months, or a quarter of a year, or something like that. And you have window features, which are basically just sliding windows, and we'll talk a bit more about that. So, sorry guys. Yeah. So what we did here, basically we created this feature pipeline, and you can look at it on the slide. It's just a dictionary definition of what operations should be applied on a time series. So, for example, we have an incoming time series, we have points coming one at a time, and we define this feature pipeline by saying, okay, we have this column, which is basically a time series, and we should apply this features as the data is coming in. So what I wanted to tell you guys, which is really interesting, is that this is the traditional example, and I'll show you how we implemented basically NumPy. And but it's really cool. You can do this actually by compiling all this information in TensorFlow operations. So this kind of feature pipeline is completely equivalent to a TensorFlow graph in a sense of the result will be the same. So that's really cool. And if you do one operation at a time, NumPy is faster. So what we do is faster. But if you have all of them, TensorFlow might be faster. So what I wanted to tell you guys about the feature pipeline. So you have this kind of a box, basically, and you have data points incoming one at a time. And you define this feature pipeline, and we apply the operations basically as the points are coming in. For example, this scaling operation, which has mu 10 sigma to 0, it doesn't matter. This is basically operation that scales some value, as you can see here. It basically flattens the value. And for that one, it's really easy. It's like calculating the sum as well, yeah? So you have a buffer, you keep the variable there, then the new number comes in to, buffer was 0, 0 plus 2 is 2, 2 plus 2 is 4, and so on. So it's really easy. But for example, you can imagine if you have values that depend on previous values or are windowed, then you need to use buffers of certain size, and you need to say state in a smart way. And what you also need to do is you need to know when to flush the buffer, revert the state from the buffer, and so on. So let's go to how this looks like. So you have, this is basically the abstract class that we started with. So we said, okay, we want to do NumPy online, and how we want to do it? Well, basically, we have these 3 methods. One of them is process, so you can define any operation, and it should be overridden. You define your own class, and you override the process and say you apply your operation, whatever that is. And the fit transform will actually apply this operation inside of a buffer, and will save the state of that buffer. And transform will just actually calculate the values and pass through the results. So it will not save the state. This is quite useful, for example, for testing purposes and so on. So this is the abstract basically way of thinking about this. And you can imagine now, if you take a look at this feature pipeline that was there, like this dictionary of things, this become these classes that are connected together. And what's really important is that they are available all the time, and they're fault tolerant in the sense that let's say that even bugs and everything happens all the time, all the time. We kind of used to it, and we collectively in silence agree that it's okay. So, but this happens, and this needs to work all the time because you're kind of using maybe even proprietary data from your customers to predict how their behavior how something of their interest will behave, and they get an email with the wrong value, and that's really when we are talking about some different aspects of world where this is used, even margin of errors of 0.01% can make a big difference. So you have to be really careful. And so yeah, the scalability. This needs to scale, and the TensorFlow I already told you guys. So you can compile this thing into a TensorFlow graph. And so when you have this one operation that is fully online, then you can define something like online n-step computations, where basically you start. So basically you start with a buffer that has some size. For example, if you take a look here, I wish I had line numbers there. But if you take a look at the self.state equals NumPy full and so on. So basically you're creating an initial state, which is just fields of nones. You don't have any data. And then basically in the process, you actually apply the operation, save the state if that's necessary, and return the transform arguments. And everything is done in a simple, and everything is done in a NumPy array. So just the result and the thing that you will probably discard just are separated by n, which is here the number of steps. And so this example I won't go in. This is, for example, standard deviation filter that you can use. This is actually an online operation. And what's really interesting here to mention as well, so we also have problems. That's the nature of the data, is that the resolution changes. So for example, you cannot expect that everything will be okay with the data, or that you will get the data that has a unique time index. In a sense that something that influences something, you may get the data point one time at a day, and you can get the minute data for something else. So you kind of need to be able, as this data is coming on, you need to be able to change the resolution. And we did the same approach, basically. This is online in the sense that it is queued, but it is queued because of the resolution, not because we cannot process it. You have to, for example, you have to queue the data if you do not have the entire week or something like that. If you have just one day and so on, you need it. So resolution specs here show you just dictionaries. Basically, you define this, and the system will accept this, and will be able to do the resolution online. And it's quite simple. We kind of omitted few methods here that are not important, but basically this you start with this, and then you create incremental resolution, and that the incremental resolution becomes a second resolution, a minor resolution, and so on. So increment is just either number of seconds and so on. So here, I guess, let me see. Here, I guess I'm going to transfer the mic to Max, and he's going to tell you a little bit more about the CLPU.
Thank you. Well, actually, we're almost done. We want to show you a video of really the vision, going back to why we're doing all of this, right? The idea is to produce a way to model the complex world around us. And so we have a kind of a cool video that I really like to show. Actually, I have it here. So what you're seeing here are essentially models that are a part of the economy. And so, this economy is massive and distributed, and it's happening all the time in real time all around us. And so the thing that you see, the network that you see here, is a network of online operations, right? It's a network of signals that are flowing between various components of the economy. And so, you have everything from finance to energy production. You've got logistics and, food production and demand. To give you an idea, if you could predict food production better, you could save massive amounts of food, which has a significant, contribution to global ecology. Predictions in logistics would also be massive. These are all actually real use cases, by the way, from real customers that we have. So all of these are real use cases. So this matters a lot. And so let's just to kind of wrap it up. Just to kind of give you an idea of, when you're building a product, you need to understand who your users are. And so we've got plenty different users, and they care about different things. You've got the business executives who have to make decisions based on these models. So these models have to be really, really robust. So all that we do because these decisions can make a big impact. We've also got data scientists who want to be more productive, and software engineers who want this whole thing to help them and get out of their way. So to conclude, we are hiring, so please feel free to come and talk to us. We have more roles than these two, but these are, I guess, the key for this audience. Yeah, thanks so much. Shall we do questions now? So so maybe we can get started from the top. I find it interesting, actually. I haven't gotten this question yet about GDPR. To be honest, we don't really do personal identifiable information, right? So it's not really a factor. However, you could say the world has, GDPR is a good example of a world-changing phenomenon, right? Because you have something that's changed all of a sudden, right? It came into effect, and all sorts of companies had to augment their processes to change the way they record data. A lot of them cannot do what they used to be able to do before. And so this is a kind of a systematic change in the world that we are talking about. So this is why you need adaptive models, because you get some kind of a point change in the world. And all of a sudden, after that change, the world, the mechanism in which some part of the economy operates has changed. And this is why we are doing all of this adaptive processing to deal with these kinds of changes. But strictly speaking, we don't do any personally identifiable information, so it's really not a factor for us. This is also a great question, the second one. The question says, do you retrain your models in fixed time intervals on certain real-world changes, or both? And how do you determine the right moment to retrain? And how long does it take? That's a really great question. Actually hits the nail on its head. You know, we are still early, and we don't. Sorry about that. We don't do everything that we would like to do. So in terms of our product right now, it can do things in fixed intervals, but what you really want to be able to do is identify when those events happen, right? In terms of the science behind it, there are many ways to do that, and we could go into details, and I'm happy to talk about it kind of offline. But really, this is key. You know, you want to know when you want to retrain. How long does it take to retrain? It's a great question. It can be a really long time. Discovering a model in an automatic way is very resource intensive. So to give you an idea, a model optimization could take days, a single model. And now you might be thinking about a whole scale of models, thousands of models. We just came yesterday from a hackathon where we built thousands of models actually in the process of the hackathon, kind of real time, you know. What's your biggest success story so far? Thanks so much for that question. The success story, really, I would say, we won the hackathon, so that was a great success story. But I don't think that's the biggest one. The biggest success story is really our customers right now. We've got 4 right now, and they are, and really the fact that they are using this on the forefront of decision making is, I think, really, really exciting. I cannot talk about the specifics of a lot of those, and I don't necessarily even know what people are using this for, but I think it's really cool that we make an impact on real-world decisions, which is really neat. Well, it all starts with a data set that could come out of Excel, right? So you've got a bunch of time series in Excel, and that's the starting point. Now the next question is, it says, you know, how are the inputs to automated data preparation prepared in your pipeline? Well, essentially they can come from API, or they can come from Excel. They are just really bunches of numbers or bunches of labels, and kind of that's the starting point. As Senad was saying, we deal with time series data, so data can be daily, weekly, every minute, and so understanding how to model data at different frequencies is a problem we have to handle. And so those are some, or missing data points, things of that sort are some of the problems that you might have to deal with when you're doing automated data preparation. I hope that makes sense. That's a really great question. Are n-step transformations strictly linear pipelines, or do they allow conditional forking of the data flow? Right now, they're strictly linear, yeah, but that's a really great question. You might want to do some kind of forking, especially in the context of what I was saying about GDPR, right? In the context of regime changes or regime shifts. So yes, you might have a reason to be building forking pipelines, but right now, no, they're strictly linear. So that makes life a lot easier. Actually, I would say we're not so exciting in this regard. We're not doing massive amounts of data. Probably the biggest data sets we got were on the sizes of gigabytes, let's say. But I would say we are more big compute versus big data. In particular, in time series world, it's not really driven by the size of the data, because most often, if you want to do any kind of modeling, you're going to have some sort of a pre-aggregation step. So there's no point in just kind of showing off and piping petabytes of data if you're actually not going to be getting any signal out of that, right? In fact, you're probably just going to be wasting cycles. So the modeling depends on how far into the future you want to predict. And if you want to predict a month into the future, you really shouldn't be piping nanosecond data. That has no effect on the month from today. Similarly, if you're going to be predicting a nanosecond into the future, you probably don't need that data from a month ago, right? So in effect, you don't have to have lots of data in this world. But there was a question about LSTMs, and they do need a lot of data. So fair enough, the data sets can get big, but not that massive. Actually, no, not yet. We have light GBM in the pipeline, but we don't have it yet. So yeah, XGBoost is what we use. I've never heard of CatBoost actually, so thanks for that. We're gonna write that down and give it a try. And this is really great. Would love to talk to you, whoever asked this question. I think it's really, again, hitting the nail on the head. Our name of the company is causaLens, and maybe this question brings up why are we called causaLens? Because we're trying to figure out causes in the world, right? We're like a lens to find the cause and effect in the world, right? And cause and effect is almost like a philosophical question. And Granger was the guy who came up with this notion of Granger causality. The idea was that if you had some kind of signal that consistently helps you predict something else, then in effect, setting aside all this philosophy, you could say it is a causal signal. It has some sort of a causal impact on the other variable. So if, let's say, if every day before when mortgages go up, mortgage rates go up, if there is an announcement by the Fed every day that preceding a mortgage is going up, then you could say that the effect of the Fed announcement is what's causing the mortgage rates to go up, right? Now, is it strictly the case? It's almost a philosophical question, but who cares, right? If this event always precedes the other event in time, for all intents and purposes, it's causal. So that's the notion of Granger causality. We use ARIMA, support vector regressions. We don't use self-organizing maps. That's great. Neural networks we use, and genetic algos is actually how we do our model optimization. So yeah, we use 5 out of 6. Any other questions? Thanks so much.
Thank you, guys.
Hi, I'm Max from causaLens. The experience at PyCon Balkan has been really great. In general, it's been really great to hear more about what people are doing in this part of the world. We personally have some really great people based here in the Balkans. They are really brilliant, super smart, and I think this whole region as a whole has some incredible creativity and superb talent. So it's been really great. The organization is wonderful, and we really benefited from speaking at PyCon Balkan today.